All right, so this video is on section 4.3, talking about measures of relative position, box plots, and outliers. So given a set of data values can be labeled x1, x2, x sub n, and that's just a count on the data values. That's all it means. So x is some number, which is a data value in the set, and then we just number them 1, 2, 3, 4, all the way to n, which recall that little n represents our sample size. So it's saying that we are counting all of the data values up to the nth value, which is the last value. The pth percentile is a value, say x, such that approximately p% of the data is less than or equal to that particular data value, and approximately 100 minus the percentage p of the data is greater than or equal to x. So to determine the pth percentile, where when we say pth, we're talking about any number, so like 80th percentile or 16th percentile, whatever it is you're looking for. In order to determine this, form an ordered array by placing the data values in order from smallest to largest, which we should be fairly familiar with from now, up until now, since we have had to order our data values for quite a few things now, including calculating class widths. To find the location of the pth percentile in an ordered array, you use the formula L equals, L being the data value that marks the specific percentile you're looking for, and you multiply the sample size times P, which is the percentile you're looking for, over 100. Where n is the number of observations or the sample size. L, if it's not an integer, then you would round up and you'd have to take an average of the data values. But actually not true. If L is not an integer and you have to round up, then that is the count of the data value in the order from smallest to largest that marks the specific percentile you're looking for. Now, if you do not need to round, let's say that L, this fancy cursive L looking thing, it comes out to be exactly an integer, then you need to do an average between that integer and the next. Let me show you some examples because that probably made absolutely no sense by just reading it. So if we're to find the 50th percentile for the following data set, we look at the data, and the very first thing we need to do is to order the data set. So let's do that. Now, because it's a small one, we'll just do this by hand. If we had a larger data set, it is really easy to do in Excel. And I would highly recommend that you copy your data from the Hawks Learning Homework, which you can do by literally there's a button that says copy data, and copy it into an Excel file. And ordering data in an Excel file is a click of a mouse, which I'll show you. But since this one's really small, let's just order it together. So we know 0 would be the smallest, then 1, then 3. We can cross these off as we go. Oh, I skipped 2, which is why I like to cross things off so that I know if I need to redo it. 2 and then 3. And then 5, 7, and 9. Now that they're in order, I count that there's 1, 2, 3, 4, 5, 6, 7 data values. So I'm going to take 7, which is n, and multiply it by 50 over 100. Okay, so the formula is the sample size, 7, times the percentile you're looking for divided by 100. So when you multiply this out, we get 7 times 50 over 100. And my calculator tells me this comes out to 3.5. So this is not an integer. Integers are whole numbers. They don't have decimals or anything like that. So because this is a decimal and not a whole number, we would simply round up to 4. And that's saying that the 4th data value in the ordered set marks the 50th percentile. So let's count. 1, 2, 3, 4. So the data value, this X value, this data value 3, represents the 50th percentile. And since the 50th percentile is also called the median, we also know that the middle number or the median of the data set is 3. All right, let's try another one. Hold on, I can't find my mouse. Okay, let's figure this out. Don't mind me. I am trying to find my mouse, which is at the moment very hidden. Okay, I have no idea. There it is, found it. Oof, my bad. That was rough. Okay, solution I still kept in there. Now, since the location of the percentile is not an integer, we rounded up to 4. We just counted the data values. Okay, we did all this part. Good. So let's suppose that 40 members of your company are given a screen test for a new position. These scores are reported in the table on the next slide. To inform potential employees of their screening test performance, you may wish to report various percentiles for the test scores. So we are charged with finding the 10th and the 88th percentile for the following data set. Now, this already got ordered through here, but again, I will show you before we finish this lecture how to order in Excel. So we ordered the data set and we know that there are 40 data values. So we're going to take 40 and multiply it by the 10th percentile, so 10 out of 100, and we get 4. So we know that this is not rounded. This is an integer 4. So in order to find the 40th percentile, we actually have to take the 4th data value and the 5th data value and average them together. So the 4th data value is the 27 and the 5th data value is 29. And let's go back to the data so you can see where those are coming from. So if we're going in order 1, 2, 3, 4, and 5, so we would take an average of 27 and 29 to get 28, and 28 marks the 40th percent or the 10th percentile, excuse me. What does that mean? That means that 10% of the data values fall below 28 and 90% of the data values fall higher than 28. To calculate the 10th percentile, oh, we just did that. Okay, so to calculate the 88th percentile, oh, sorry. Okay, here we go. 88th percentile, I take my sample size of 40 and I multiply it by 88 out of 100 to get 35.2. Now 35.2 is not an integer. We have to round up to 36. And so no average is needed. We will take the 36th observation or data value in the set, in the ordered set. And the 36th value is 73. So 73 marks the 88th percentile, which again, that means that 88% of the data values are below 73 or less than 73. And the complement of that, which if you take 100 and minus 88, you get 12. So 12% of the data values are larger than 73. So the percentile of some data value X is given by, so let's say, for example, you know that you got an 82 on an exam and you know that there are 24 people in the class. So you might want to know what your grade, what percentile your grade would be. But in order to do that, you would need to see all the grades. You would need to know how many of the grades are below what you got on the exam so that you could calculate what percentile you are. Let's take a look. Now, specifically, there are some very, popular, I can't think today, very popular percentiles. They're called quartiles, and that's the 25th, the 50th, and the 75th. So that should sound familiar. If you're thinking about a dollar, it's like the quarters on a dollar. And it's really helpful to draw a new chart that we haven't looked at yet, which is called a box plot. Now, the interquartile range, IQR, is simply subtracting the 75th percentile from the 25th percentile, which results in the middle 50%. That's useful when the range is not useful. For example, if a student in the class got 100 on an exam and another student in the class didn't show up and got a 0, the range would be 100 minus 0, which is a 100-point spread. That tells us absolutely nothing about the data. We would know that the students are within 100 points from each other, but that's kind of what we would have already known if we weren't even looking at real data values before they even took the test. But if we've calculated in the same data set the interquartile range, and let's say that the 75th percentile was marked by a grade of an 80 and the 25th percentile was marked by a grade of a 70, then we would say that the inner 50% of the class got within 10 points of each other on the exam. Now that says a lot more. I can picture half the data points clumped together between a 70 and an 80 versus saying that 100% of the data values are within 100 points from each other. For a set of data, what we call the 5-number summary consists of the minimum, the maximum, and those 3 quartiles, the first, the second, and the third. Now, the 50th percentile and or second quartile is also called the median, the middle value of an ordered set. So where would we use these quartiles? Let's actually practice these quartiles, but let's use the little data set that we had. Hold on, going back. Here we go. Back to this data set. So let's order it first. So we've already done that before, but let's do it again. So we have 0, 1, 2, 3, 5, 7, and 9. Now, in order to identify the 5-number summary out by hand, which Rguroo does this for you, and I'm going to show all the Rguroo stuff at the end of this video, we have our min and we have our max. So we know that our min is 0. Q3 we need to find. And we know our max is 9. So now we already know the middle number actually is 3 because we calculated the 50th percentile. But if we wanted to, we could slash off on either side. So 0 with the 9 and so on going through. And we'd find the median or the 50th percentile. Then we would have to, let's see if we can, no, all right. Now what we'd have to do is we have 0 and 3. So now we take an average to find Q1. So we'd have 1.5 is Q1. And here we would have an average of 5 plus 7 divided by 2. And that gives us 6. And that's how I found 1.5. I did 1 plus 2 divided by 2. So now I know that Q1 is 1.5 and Q3 is 6. What does this mean? It means that 25% of the data values fall below 1.5 and 75% lie above. 50% of the data values lie below 3 and 50% lie above. 75% of the data values are less than 6 and 25% of the data values are greater than 6. 100% of the data values are smaller than 9 and 0% are larger. Okay, now I'm having technical difficulties because I cannot find my mouse. Here it is. Okay, let's head back to where we were. So excuse all the skipping. We already covered this. Oh, super clicker, my bad. Okay, BoxPlots. Now, that was a 5-number summary, and we can apply that to what's called a box plot. Okay, so if we look back at that data set, we said that the minimum was 0, Q1 was 1.5, Q2 or median was 3, Q3 was 6, and the max was 9. So if we wanted to draw a box plot for this data set, the number one thing we have to do first is create a number line. And the number line needs to at least extend from the min to the max. I'm going to go 0 to 10 to make it nice and even. 1, 2, 3, 4, 6, 7, 8, 9. Okay. Now, what I'm going to do is I am going to draw my box. Now, my box is the interquartile range, which is between 1.5 and 6. So 1, 1.5, and here's 6. So I'm going to draw a box for the interquartile range. So the box of a box plot goes from Q1 to Q3. Then you take the median 3, 1, 2, 3, and draw a straight line. Then you extend your whiskers to the minimum and the maximum. And then you have to identify what you've just learned. So what have we learned? Well, in this space here, this is 25% of the data, the smallest 25%. This little box is 25%. This much larger box is still only 25%. And this whisker here is also the top 25%. Now, why is this helpful? Well, take a look at the spread of the data. So I can see that the lower 50% has a much smaller, it is crunched closer together than the upper 50%. You see how we have a lot more room here than we have going on here. What that tells me is that 50% of the data values are clumped really close together on the bottom half, while the top 50% are a bit more spread out. So if I was talking about, well, what is the shape of the distribution of this data, it would be skewed left. A little bit messy, but hopefully it helps. Okay, so we are skewed left. Okay, just give me a moment to find my mouse again. Oh, found something. Oh man, what the heck? Sorry guys, I don't know why my mouse is having issues today. It's there, it's just not necessarily showing me where it is. Well, apparently I'm still doing things as I'm clicking. Okay. Oh, there we go. Sorry about that. Okay, so if we're taking a look at another example of a box plot, when I'm reading this box plot, I see that the minimum value in the data set is 18 and the maximum is 82. I see that the median or the middle value is 54, which again, that means if 50% of the data values, screening test scores are below 54 and 50% of the test scores are above 54. Now, looking at the size of this tail, this box, the blue box, and the other tail, they're all pretty equal in width. Maybe some of the whiskers or the tails are a little longer, but this data looks pretty symmetric. It's not skewed on one side or the other. It's not squished in one quartile over another. So I would say that this data set of test scores is approximately symmetric. Okay. Now, determining the 5-number summary is the first step for drawing a box plot. And then you have to draw a number line. That's really important because anybody could draw a box that's symmetric and then label it. and that kind of defeats the purpose of seeing what the shape of the distribution is. Construct the box as I showed you from Q1 to Q3, draw a line vertical through the box at the median, and then extend the whiskers to the minimum and the maximum. Now we're going to use our Rguroo to build our BoxPlots, which I will do in a moment. There's a data point that's considered an outlier if it is 1.5 times the interquartile range above the 75th percentile, and symmetrically or similarly, 1.5 times the interquartile range below the 25th percentile. That's how we would identify whether a particular data value is an outlier or not. Education attainment seems to have a positive association with a person's income. The amount of education a person has can be divided into 5 categories. Less than a high school diploma, high school graduate, no college, some college or associate degree, bachelor's degree only, advanced degree. The categories are ordered according to educational attainment. The vertical box plots in the figure on the next slide show the distributions of personal income per each level of education for individuals age 25 and older. Rather than extending the whiskers to the smallest and largest income values in each category, the whisker endpoints represent the 10th and the 90th percentiles. What conclusions can be drawn from this figure? So if we take a look at this figure, we are looking again at the weekly earnings depending on education. So remember, where the blue and the pink meet is the median line, so the median salary. And we can see that it is steadily increasing as you get a different degree. And there's quite a difference between an advanced degree and less than a high school diploma's median weekly earnings. We go from 500 a week to about 1,500 a week, which is a huge difference. We can also see by the whiskers that although the minimum does rise, the first 3 options, the minimum is fairly the same. While it starts to clearly show a difference when you have a bachelor's or an advanced degree, that your minimum salary is even higher than the median salary of a high school diploma, or less than a high school diploma. Now, if we look at the upper end, our 90th percentile markers, we can see that there's a huge difference when you have an advanced degree or bachelor's degree, and where the limit is, where the sort of glass ceiling, when do you bottom out and stop making so much money? Remember, these aren't the maximums, because the max and the min are likely to be outliers, which is why they're left out of these box plots, and they're only looking at 90% of the data. It is rather obvious from this figure that more education equates to higher earnings. Also, there is a lot of spread in the last 2 boxes, and not so much in the first couple boxes. So we're talking about the heights of them. So if we looked back at the graph, notice from the 10th percentile to the 90th, there's not much spread. We're from, I don't know, maybe 400 to 1,000. And if we look at this last spread, we are going from about $750 to a little over 3,000, which is a much larger spread. This is probably due in part to the market demands for degrees in scientific disciplines, especially computer science. So one of the last things we want to talk about in this section is a Z-score. Now, a Z-score is also called a standard score. I'm going to end the show before I don't lose my mouse again. That's quite annoying when I do that. Hold on. Here we go. So if we are looking at a Z-score, I want to show you where the Z-score lives. The Z-score lives on what's called a standard normal curve. I have no idea where that line came from. There we go. Ignore the line. Now, the standard normal curve is called standard for a reason. The center of this curve mu, the average of a standard score, z, is always 0, while the standard deviation, sigma, is always 1. So if I was to draw like I would draw from the empirical rule that we learned, I would be counting the standard deviations, and it's a very simple count because it's always a standard deviation of 1. And we could plot z-scores anywhere on this curve by using this formula. The data value minus mu, the average of the set, divided by the standard deviation of the set, will tell us exactly where that data value falls. So for example, if I was curious on whether my height was unusual or not, and let me give you some references on what's unusual and what's not. So between two standard deviations, either way, above or below the average, this is the usual range. So we would find typical values to be within two standard deviations about the mean. Now, between 2 and 3 on either side is where we start to see a little bit more of the unusual data values. They're kind of far removed, but not so far that we would call them outliers. Not until we get beyond 3 standard deviations. Once you get beyond 3 standard deviations, we are very unusual, and we would call these outliers. Okay, so if we were to do the math and multiply 1.5 times the interquartile range and add it to the 75th percentile, we would find data values that fall outside of 3 standard deviations. And if we multiplied 1.5 times the interquartile range and then subtracted it from the 25th percentile, we would find these outliers in the lower range over here. Suppose you scored an 86 on your biology test and a 94 on your psychology test. The mean and standard deviations of the two sets are given in the following table. What are the z-scores for your two tests? On which of the tests did you perform relatively better? All right, let's do this one. So let's first calculate a z-score for biology. So z for biology, we're going to take the data value, which we scored an 86 on the biology test. So we have an 86. Subtract the mean. The average test score for the class was a 74. And divide by the standard deviation, 10. So if we enter this into our calculator, and we enter 86 minus 74 divided by 10, we get a z-score of 1.2. And it's positive, so what we can interpret is that it is above average, and it's a typical score. An 86 is not unusual. I'm right in the range of everyone else. How do I know that? Because the z-score is within 2 standard deviations. Now let's calculate our z-score for psychology. So z sub p. I got a 94 in the test. Subtract the average in the class, which is an 82, and a standard deviation of 11. So I'm going to do 94 minus 82 divided by 11, and I get a z-score of 1.09. We're on the same spot, so I did typical on both exams. I'm above average, not by much, on both exams. But if I was to look at the standard normal curve and compare these two z-scores, here's a standard deviation of 1, and here's a standard deviation of 2. So 1.2 would be about here. That would be your biology z-score. But the other one is not that far below at 1.09, and that's your psychology z-score. So if you were looking at this, 0 is you did average, and anything to the right of 0 is you're above average. So the farther above 0 you are, the more above average you did. So that would mean that by a very slight margin, you did better on the biology exam than on the psych. and that is in reference to the rest of the class. Even though the raw score of the psychology test is larger than the raw score of the biology test, relative to the means and variability of the data sets, the performance on the biology test was slightly better. Once again, changing the scale of the data has beneficial effects. It enables the comparison of the two measurements that are drawn from different populations. So what this is saying is if you would have looked at your two tests, your psychology test you got an A on, 94, while your biology you got, what was it, an 80 something, an 86, a B plus. So you might automatically have thought, oh, I clearly did better on my psychology. But if you were trying to say which one did you do better based on the toughness of the test, they were two completely different tests. So comparing the scores directly is not actually that fair, which is why when we compared the standard deviations, because that accounted for how the rest of the class did, which accounts for the toughness of the test, we see that we actually did better on our biology test. So some properties of a z-score. If a z-score is negative, the corresponding data value is less than the mean. And conversely, if the z-score is positive, it is greater than the mean. The z-score is a unit-free measure, so there's no inches or miles or anything on z-scores. That's why they're called standard scores. And we use standard scores to compare a bunch of different data with different units. So if I wanted to know what's more unusual, my height, my weight, or the hours I watch television, I could translate all of those into z-scores and see which one is farther away from the mean. Okay, now let's take a look at Rguroo. But before we do that, let me first show you guys how to order data values in Excel. I probably should have done this a long time ago, but I apologize, I didn't think of it. So I'm just going to grab a random set. Let's employee ages, and that's what I'll use in Rguroo as well. And let me share my Excel file. And I'm just going to quickly show you how to order a data set quickly in Excel so that it will make your homework hopefully much easier to do. So in Excel, you just take your cursor, click and hold and drag, highlight your data values. Then you're going to come over here to the A to Z filter and click smallest to largest. Fastest way to order a data set. Now, that's if you were doing some calculation where you needed to order the data set. But if you were doing the 5-number summary or anything of those types of calculations, Rguroo does that for us. So let me show you how to do that. Now, this is no different. I've actually showed you this before, but it doesn't hurt to see it more than once. Hold on, I just got to find the right screen. Here we go. All right, so I'm going to log into my Rguroo account. Now I've already uploaded a data set. I'm going to use the data set I already have in here. But let's say that I wanted the 5-number summary. So I would go to Data, come over here to Functions, and do Summary Statistic. Now, it's a summary statistic because it only does these calculations for sample data. If at any time you're told that there is a population data set, unfortunately, Rguroo does not calculate that. They will in the next update because I contacted them and asked them, why don't they have that option? And they said they're working on fixing that. But as of right now, we only can calculate sample statistics, which 99.99% of your problems are samples anyway. So hopefully this will not be an issue until the update. Let's select a data set. I'm just going to select employee ages and identify that the variable I want an average in all the 5-number summary is ages. Minimum, quartile 1, quartile 3, medium, which is quartile 2, and the maximum. I can get the mean, I can get the interquartile range, the standard deviation, and the variance. Depending on what the question is asking you to find, you now know all the different things that you can find in this little summary statistics screen. Then we hit the eyeball. Now, Once you get here, it looks like nothing happened, but all you have to do is click on all observations, and you see that there are 24 data values in the set. That's little n. The minimum employee age is 16, and the maximum is 63, with a median at 26. The mean is 31.792. The range is 47 years between the youngest employee and the oldest. The interquartile range, the amount of years between the inner 50% of the class, of the employees, is 24 years. There's a standard deviation of 16 with a variance of 263. Now, if I wanted to take these data values and create a box plot, I'm going to go over to Plots. I'm going to go to Create Plot. I'm going to click on Box Plot. We are going to go and select our data set that we would like to create a box plot for. We then want to say, hey, which variables? Notice that once I select the data set, it automatically will list all the data values, all the variables in the data set, which in my case, I only have one. So I'm selecting ages. I move it over to selected. The title of the box plot will be employee ages. Remember, if you forget to title, you can always go back by clicking basics after you've created your graph. The x-axis is going to be years, and there really isn't much for the y-axis for a box plot. We are only labeling the numbers on the number line. Let's show, no, we don't need to show the mean on it, and our eyeball. Now I see that it's a vertical box. I'm not a fan of vertical boxes, so I'm going to go back to basics, and I'm going to say, you know what, I really do want it to be horizontal. I just think it looks better. So I can see now the shape of the data. It wasn't necessarily that clear when we were just looking at the numbers of what the spread is. But when we graph those 5 number summary, we see that this lower 50% is much squished together than the upper 50%. And these are the same count of data values. So this set has 24 data values. That means 12 of the data values exist between 16 and 20 something, and 20 something, this median, and 63 is also 12 ages spread out. So we can see that the younger population, or the lower 50% for ages in these employees, are closer together, while the upper 50% are much spread farther apart. This concludes our lecture on 4.3